Great. So second last topic. It's pretty exciting. Second last topic. So we got this, and then multiple regression, and we'll be done. So today we'll talk about correlations, which you guys have all run into correlations before. You probably talked about them in other stats classes, and probably regression too. But just like with ANOVA, we're going to talk about this from a different angle, I guess you might say. So everything we've talked about so far has dealt with differences between means, right? It's all about differences between means. You can look at this in a mean difference, like you have, say, two groups, three groups, whatever, but even in the simplest case, two groups, as a relationship between the independent and the dependent variable. Okay? So you can say there's an effect of whatever the factor is, whatever the variable is, but that really means that as one changes, the other changes. When we first started the course, and I was talking about covariation, that's what we're talking about, two things varying together. So you can look at this as a relationship between an independent and a dependent variable. You don't tend to think of experiments with two groups or five groups as relationships like that, but they really are, right? So with a continuous or discrete variable with many levels, so either a continuous variable or a discrete variable with many levels, you can see these relationships a lot more clearly. So here's an example. There's a scatter plot of some made-up data. There's no way that IQ correlates that highly with income, if only it were true. So I made up some numbers. There's no way that's that. There is a pretty high correlation as far as correlations go between IQ and income, so 0.5, it's really high. But that's way more than 0.5. Anyway, we see a relationship there. We see that as IQ increases, income increases. I don't know what we're measuring income in there. Tens and thousands of dollars, I guess. That's probably right. Move that over here. The scatter plot, of course, is a useful exploratory data analysis tool. Whenever you're collecting a lot of data, you're going to look at scatter plots. That's just a thing you're going to do. But it can also be a way of testing a hypothesis in a way. What we want to do is standardize the variable relationship, even if these are on different scales. So if we're measuring IQ with, let's not use IQ, let's use the income one. If we're measuring income in the number of pennies you make per year, or the number of dollars you make a year, we don't have pennies anymore. Nickels. The number of nickels you make a year, or the number of dollars, or the number of pounds sterling, or euros, or whatever it is, it shouldn't matter. Or if we're doing a correlation between your height and your weight, it shouldn't matter if we're measuring your height in centimeters or inches, or how many pennies tall you are. Pile of pennies. It's a really strange way to measure something, but how many pennies tall are you, sonny boy? That's what they used to do in the old days. Or in the UK, they measure your weight in stones. There's 14 pounds in a stone. What happens when you get like an ancient civilization? They're like, yes, we've always measured it this way, and we always shall. So, but it shouldn't matter if we're measuring in stone, or in kilos, or in pounds. As an aside, does anybody here actually know their weight in kilos? And you probably do because you're a wrestler. Right? Mm-hmm. Yeah. Anybody else know their weight in kilos? Really?
Yeah.
Wow.
1 kilo is 2.2 pounds.
Oh, I know that. Well, I can do the math. I can do arithmetic in my head and everything. But
I do it for my dogs. I give her own drugs.
Very good.
So I have to measure.
Okay. We've been metric in this country since 1974, and we still use height and weight in pounds and inches. I'm just screwed. I'm right at the right age where they taught us imperial until grade 4, and they said, well, no, don't, forget that stuff. So I'm just a hodgepodge of strange things in my head. Right? Generally. I was saying to my daughter once that I was putting out a floor, and I said I needed a piece of tile, can you go see if there's a scrap that's, about 3 5/8 inches? And she said, I don't know what that even means. And I'm like, okay, so that's going to, is it about I don't know, somewhere around 10 seconds. Just go find something. I'm just confused, generally. So, but back to standardizing things, let's look at how much variance two things share. And this will still this is still going to, because variance is affected by the unit. The number we get here with something like covariance, which is the sum of the x's minus x bar, and the sum of the times the y minus y bar. So that's for each data point. You do that. Divided by the number of observations minus 1. It looks a lot like a variance, except instead of x minus x bar squared, it's x minus x bar times y minus y bar. That's still going to be affected by the unit size, but at least it's a start. So this measures the degree to which two variables vary together. That's why it's called covariance. Okay. Oh, what happened there? That was weird. Now, what it said, let's go back to that. Why did it do that? That's really strange. Okay, I'm going to just read it from here. So if deviations from x bar and y bar go in the same direction, you get a positive covariance. And if it goes in the opposite direction, you get a negative covariance. So if as x goes up, y goes down. So you can think of variables like that. I don't know, what's something that has a, well, positive correlation is easy. That's weight and height. That's trivial. That's an easy one, right? So as weight goes up, height goes up. What is something as something goes up, another thing goes down?
Kilometers driven and gas left in the tank.
Good. That's great, actually. Yeah, that's perfect. Kilometers driven, gas left in the tank. Or miles driven, and gallons left in the tank. Great. And it would change the covariance because variance is changing, right? Based on those it's a really good example of these in the future. For variance changes, so the covariance will change. We want to standardize this, a standard measure of association, so we don't have to worry about the scale. So I can say that height and weight, no matter if you're measuring it in height and how many pennies tall you are, and your weight in stones, or I'm measuring your height in centimeters and your weight in kilos, like a civilized person, which means I'm not civilized, by the way. We want to standardize it so the scales don't matter. And the way we do this, well, covariance depends on S sub x and S sub y, right? How spread out the x values are, and how spread out the y values are. So why not just divide by the product of those things, right? So that's what we're going to end up doing. Whoops, and then it just goes black. Wow. That slide projector's weird today. So why not just divide by that? Okay. That was weird. So we get the Pearson R. And R equals the covariance of x and y divided by the product of S sub x and S sub y. Which is why it's called, the official name is the Pearson product moment correlation coefficient. No one calls it that. Usually it's Pearson R or just R. Okay. So if the covariance of x and y, the absolute value thereof, is equal to the product of the variances, we're going to get 1. All that says is if their covariance equals multiply the two variances together, it's obvious that they're overlapping. They're measuring the same thing. So if we had height in centimeters and height in inches, the covariance is going to be 1. And so with the product of their two, the covariance would be 1. But the covariance divided by the product of their variances would be 1. You'd have what's called a perfect relationship, which we're all really trying to have. Me 30 and a half years. The sign of R, which sounds like the name of a bad B horror movie, it's the sign of the R. In a world where correlation coefficients can only be between 0 and 1. Negative 1 and 1. Lives a man. Who's afraid to love? I don't know. With the courage to calculate residuals. So the sign of the R only shows the direction of the relationship. So it doesn't say. So for example, if I said I had 3 correlations that I calculated, positive 0.4, negative 0.7, and positive 1.25, which one is biggest? Well, first of all, 1.25 you made an arithmetic error, so that's not even a correlation coefficient. The biggest one is negative 0.7, even though it's got a negative value. Right? So the negative just means it's going downhill, positive means it's going uphill. It's all it means. Okay. R can be between negative 1 and positive 1, but the sign only indicates direction of the relationship. Okay? Yeah, I know you guys have all heard this before. You may have even seen that very question on a quiz in Stats 2126, if Dwayne's still using my old quizzes. Okay. So it's only straight lines. This only works for straight lines. So if you had something like, linear relationship. So if you had, I don't know, so whatever y and x are here. You had that. For those of you listening on the audio, I've just drawn a perfect something. So we got there sort of an upside down parabola, which would be a semicircle. That's a beautiful relationship. It's great, and you get a correlation of 0 with that. Actually 0. Right? That's going to get you 0. There are correlations that you can do that are called curvilinear correlations. Those are totally reasonable. They work under the same kind of principles, but they don't assume a linear relationship. This all assumes a linear relationship. All the math behind this is assuming a linear relationship. Okay? Good enough. So you need a straight line relationship, and a lot of the variables we deal with are pretty straight, so we just let it go. Right? There's a lot of variables when you get into things like behavioral ecology, stuff like that, where it's actually not, you end up with really interesting sort of logarithmic curves, things like that. You just fit a different kind of curve. The logic's the same. Okay. You know, it'd be really cool if we could predict y from x. But before that, any questions so far? Pretty sure this is review, but it was a long time ago for some of you, so ask if you have any questions. You good? Yeah, okay, you've seen this before. So, if we could predict y from x, that'd be great. Basically just drawing a line through a scatter plot. So the idea here is we draw a line through a scatter plot. And I'll draw another. Let's just change this one here because I have axes up here already. No, let's do a new one. What the hell? So we've got doing a song there because I got to do something to keep myself entertained at this point of the year. I've lost any enthusiasm for doing anything for people. But see, I admit things now. You've done the evaluations. I don't care. You're doing a great job. Thank you. Great time. So
Fake it till you make it.
that's the story of my freaking career. So no, believe me. Anybody who's, and I'm not saying that I'm not good, but anybody who's we all have imposter syndrome really badly. My old postdoc supervisor, who literally helped invent the idea of studying animal cognition, said to me when I was at a conference, and if you took animal cognition, you heard this, but he said to me at a conference about 5 years ago, he retired. By the way, he retired, but he still has a lab of graduate students. And an intern, and he edits a journal. But I see him, and he said, I'm really sad I'm retired. I said, well, it's great, congratulations on the retirement, And he said, well, I'm kind of sad that I'm retiring because I'm finally doing some good work. And I looked at him, and he's a very kind of meek, mild guy also. He never knows what to make of me and to predict any of my behavior. But I looked at him, and I would never touch the guy. I grabbed him by the shoulders, and I said, do you know who you are? So, anyway. How are we going to fit a line here? Well, we could draw, we could do it by eye. Why not? That's a good one. Sure. Well, maybe that was a bit better. Maybe this one. Some would be bad. That one isn't good. We could do one going the wrong way. That's not a good one, but it's still a line. We could exhaust all the degrees of freedom and just connect all the dots. Look, I predicted it perfectly. All I needed was all the values first. And I can perfectly predict. You don't want to do that. You want to have something where I can say, we all agree on how to do this, and we're going to come up with a system. Right? So you want something that has very few degrees of freedom. Right? That it's fixed, that there's a fixed way to do it. And of course, the most common way to do this is what's called a least squares regression line. Okay? There's other ways to do it. This is just one that everybody agrees is pretty reasonable. But there are other ways to do this. But you don't run into them in anything that any of us will ever do. They show up in very esoteric sort of statistics examples. Or sometimes, it's very rare that they show up anywhere else. So, here's the idea. If these are data points here, these sort of very light, sort of gray looking deals, so those are y's, we then get a predicted line. And prediction is indicated by the circumflex, by a hat. Right? So it's called y hat. And I wondered for years if in French they called it y circumflex or y chapeau. Turns out, they say chapeau. It's really great. Or very often they just say y hat. Because everything in science is done in English, basically. But I asked with 2 French exchange students last year in the class that were like 3rd or 4th year biology students in my brain behavior class, and after class, I said, you guys did stats, right? What do you call that? And they emailed their friends. They say chapeau. They say circumflex.
But they couldn't answer because one of my best friends in Sudbury is francophone and she did stats all the way through with us.
Yeah.
For job requirements.
Okay, that's good. I applied for a job at Laval years ago. And I said, I teach in French. It would have to be very technical things for a couple of years. But then I can do other stuff. I said, I teach stats tomorrow. That's not a problem. Then I thought, so what we have here is y hats. Was the prediction. Y are the actual values. These are mistakes. Those differences between y and y hat are wrong. They're prediction errors. Okay? So what we want to do now is minimize these. And what we're going to do is we're going to minimize the sum of those things squared. Oh, sums of squares. Just when you thought it was safe to go out, they pull you back in, right? You thought you were out. They pull you back in, right? So that's what happens. So we're going to basically, the way this technique works is it, behind the scenes sort of, fits a line and minimizes that quantity. And if you remember doing math in high school, finding the minimum of a set of equations is actually really easy to do. You probably remember how to do it, that's fine, but remember doing it. It's mechanical. So what we're going to do is minimize the sum of y minus y hat squared. Okay? So what you end up with is a prediction equation. It looks like this: y hat equals a plus bx. So y hat equals a plus bx. So that's the predicted y. That's y hat. That's the line. Equals the intercept. That's where x equals 0. Plus some value b, which is the slope of the line, times x. And yes, I know in school we were taught that b was the intercept. Oh, that's not how it works anymore. So you're going to be talking about y equals nx plus b. Well, and you know what's the worst thing? I'm going to change the name of this next lecture. I'm going to change the name of A to B sub 0, and I'm going to change the name of B to B sub 1. So it's either B sub 0 or A, and B or B1. Okay? In a more general case. But right now, for our purposes, this is fine. This is the intercept. This is the slope. All right. Good. Questions on that? You might wonder how we get these values. No one does them by hand. You can. I mean, think what we have to do this. To work out this, you're going to need the correlation coefficient, or you're going to need the covariance. So you have to work out covariance by hand, and this is usually a scatter plot of hundreds and hundreds of values. So you'd never do this by hand. But if you were, you might be getting like 30 values, and you might be in statistics 281 in 1985, and Dr. Vernon tells you to do this because it's an assignment. And you go, great. It's in the library of Western working this out. You're all different answers because you all make mechanical errors because you're doing 25 of the damn things. So you take B is the covariance of x and y divided by the variance of x. That's going to give us the slope, right? And then A, we're just going to rearrange the values. And we're going to get y hat minus b times x bar. That'll give us A. Okay. So the nice thing here, you can see that B is going to have a positive or negative slope because it's got a covariance divided by the variance of x. So if the slope's positive, it's going to go uphill. Slope's negative, it's going to go downhill. Right? Very good. Easy to do.
The y and the x there, that's y bar and x bar.
Yeah.
Y hat.
Not y hat, that's right, y bar. So it's the average y value, the average x value. Well, this actually makes a lot of intuitive sense to me for some reason. The average y minus the average x times the slope, well, that's going to be where it hits. Yeah, it just makes sense to me. I've been doing this a long time, that's probably why. So one could work this out. All you need to work out this is you need covariance or s squared. Then you can get this. Because you've already, to do the covariance, you need y bar, you need x bar. So really, once you've worked out B, A is trivial. It's just trivial arithmetic. But it's still annoying to do by hand. And no one does this by hand. So if you're doing regression, you take a look on SPSS or PSYC or JASP or whatever the hell you're using, and you just pick regression and you say what the predicted variable and what the predictor is, and it'll just do it for you. And each record is one of the data. Let's say it set that up. Okay. There's an it's sort of an intuitively pleasing notion that where x equals 0, the intercept is somehow meaningful, and it usually isn't. So I talked about the guy I know that is disgraced, who collected really a great data set, though, about people smoking. And he was trying to predict how many cigarettes you smoke per day using behavioral measures that you can self-report rather than giving a spit sample. Because it's easy to do a spit sample. Because you get cocaine, which is a stable metabolite of nicotine. You ask them how, you can just see how much of that they have in their saliva, and you can guess how much they smoke. That's easy. It's also annoying for, let's say, an MD to do this. They have sent away to a lab. Instead, wouldn't it be nice if you could just pick a variable or two and say, what are your responses to these questions? And then you can know, oh, that's how many cigarettes that person smokes a day. It'll be as accurate as taking the amount of salary, nicotine, and cocaine. That'd be great. And he actually did that. And I talked about, early in the course, I talked about how in that data set, there were outliers. For example, the guy that had written in 400 cigarettes per day when he smoked. and that was probably a coding error, it was probably 40, which is still pretty heavy smoker with 400, there's no way he was alive. That's a dead guy already. And you come up with an idea, and you say, how many cigarettes you smoke per day? Maybe it's equal to some value, some base value, that's the intercept, plus, let's say it's something times your age if you're a smoker. Let's just make that up. So let's see. That means that when the intercept equals 0, that's when people are first born. So most people that are first born are only smoking 17 cigarettes a day. That's not a very meaningful, it means nothing. It's just where a line goes into a curve, it's an axis. Right? It doesn't actually mean anything. Okay? So the intercept is not always going to be some reasonable value. On the other hand, sometimes it is. Sometimes it is. So you can work out, for example, I don't have the exact numbers in front of me, but if you look at how our pay scale as faculty here works, it's basically a regression equation. It's different for different ranks. Okay. But if you're, and I'm going to make up numbers here because I actually don't have the pay scale in front of me. But if you're an assistant professor, right, it's basically, so it's going to be A plus BX, and we have a floor, the lowest you can be paid. I'm going to make up a number. I literally don't know it, because again, that's not my rank, I don't care. Let's say it's 70,000. And then we would say plus, let's say it's 2. I don't think it's 2 either. Every year you are at that rank, you get 2,000. It's not quite that same. Yes, but
can you explain to me why somebody would think that was meaningful?
in this case, it actually is, because if you say you're starting as an assistant professor, you make $70,000 a year.
So the only time it's not used meaningful is when X is 0.
It's when X is 0, it isn't always going to be meaningful. Like I said, because if we had something like let's say we were measuring, I don't know, sexual activity again, and we start saying, oh, the intercept, and that's what, babies? No. 0, no, bad. You wouldn't even start interpreting it that at like 2 and 3 and 5 and 10. You'd want to go maybe 18, just to be safe. Right? So you can come up with an equation. You can come up with an equation, but that doesn't mean anything. It's just where it's where it ended up, and it's usually because what you're doing is you're going outside the range of the data you have. So the range of, let's say, the smokers, right? Their age, and it's not nearly as easy to predict as some number times the number of how old they are. But if it were, it's people over, let's see, when data was collected in 1987, so I think the smoking age was 14 back then. The world was a little more, yeah, you could buy cigarettes. When I was a kid, I used to go to the corner store and buy cigarettes with my dad. It was 5. Yeah, ride my bike down Finch Avenue in Toronto. I'm legally blind. Hey Dave, here's a buck. Go buy me some smokes. Come back with 2 bags of cigarettes, and I have enough change to buy a chocolate bar, a Coke, and a 10-cent bag of chips. And you look up and go, 2 more 10 filter cans, please. Here you go, kid. No problem. Then they had the rule later, if you were under, I think, 12, you had to have a note from your parents that you were buying smokes for a parent. That was the rule. And then eventually went to 14, then 16, then 18, then I think it's 19. You should watch Mad Men. The world's way different than you think it was. It was way different. There were signs in here that said no smoking, which tells you something. That means there was a time when people smoked in class. Because if you had to tell people you can't smoke anymore, that means that people thought you could smoke.
Well, now we're going to this circle and you're telling people not to vape, where could they go?
That's a whole discussion we could have. In fact, frankly, the exhaust is H2O, so I don't see why it's a problem. I just think people look like idiots. Oh, look at you. Oh, where are you from? The future? What are you, a time traveler with your electric cigarettes? I always think people think they're time travelers. Hipster time travelers. That's what I did in my intro class once. I thought, because years ago, that's weird. I'm just going to let it go, but it's weird. And after class, I said, probably shouldn't do it. Somebody's going to manage it. course, you can smoke weed anywhere, but just not tobacco, you're worse than Hitler. But anyway, the point is that we're going outside the range of the data we collected. So we can't talk about somebody who's 0 years old. Whereas predicting someone's salary, there are people who have 0 years of experience.
So it's just your floor value,
It's,
which can or cannot be meaningful.
yes, exactly.
Okay.
It's just where x equals 0, where it hits, where the line hits the axis. So the worst thing you can do here is, and it's also only linear relationships. Okay? It's only linear relationships. So again, only straight lines. So if you tried to do a least squares regression line here, and I can show you why this would work, what you're actually going to get in this case with the parabola kind of deal here, that line underpredicts as much as it overpredicts. I have minimized the sum of the what are called residuals, 1 minus y hat. You can see that, right? Just that at the beginning they're below, in the middle they're above, and at the end they're below again. So you can see why it actually works out that has a correlation of 0. A regression line that's a straight freaking line, saying there's no relationship, yet there clearly is one. There clearly is one. So how do you know you have a linear relationship? Well, first of all, look, when you're doing what's called simple regression, you would have done an exploratory data analysis, you look at a scatter plot, and if you see that, you don't do it that way. But one of the things you can look at is something called a residual plot. So what a residual plot is, can you see if I'm here? It's the residuals, sorry, it's the residuals, that's the predicted y, that's the y minus y hat. They're called residuals, or E, error. And this is going to be your x variable on the x-axis. It should be pretty much randomly distributed around 0. And right now you say, well, why would I do that? Why wouldn't I just do a scatter plot? You're right. But let's say we have more than one predictor variable. Then the world gets complicated. When we talk about multiple regression, that is more than one predictor variable. It can be up to, well, it's p minus 1 predictor variables. The covariance of x and e, the residuals, should actually equal 0. So one of the nice things you actually can do is calculate the residuals. You can get, once you find out what the mean is, you can actually just transform and make another variable, and then do the covariance between x and residuals, and it should be 0. Or it should be very close to 0. It's usually not going to be dead on 0, but if it's close enough for rock and roll, you're fine. You look at it and go, okay, yeah, we're fine. And as I said here, I don't know why that just disappeared. Probably doesn't on the recorded video. I don't know why this is happening. Don't go outside the range of your prediction. That's where usually the predicted, where the intercept stops having meaning. Right?
Wait, say that again?
Well, the intercept stops having meaning when you go outside the range of where you're collecting data.
Yeah.
Right? Well, it's like saying, for example, if we're going to predict height from weight, that's in fact when you go to a doctor, and you especially do this to kids, you also might do this as an adult, and they weigh you and they get your height, and then they'll say you're at the right weight for your height. That's just that's regression. It's a simple regression. But if you know you were 400 feet tall, you should weigh 32,000 pounds. That doesn't make any sense. Right? Or, you know, if I just worked here for 2,000 years, think of how much money I'd make. It doesn't really make a whole lot of sense.
So keep it relevant.
Keep it within the range that makes sense, the range where you collected the data. Right? Now with the salary scale thing, in fact, there's a ceiling. You can't go any higher than a certain amount. For each different range. If you're interested, you can go read our collective agreement. It's really fun to read. It's great. It's great. It's nothing better than reading a union contract. It's nothing better. I was, whenever we get the new thing, I just go to the back. Oh, okay. Because go to the salary calculations. Or, no, that's insulting. No. Sort of what we went through last year up until right around now. Right? We almost had a strike last year, remember that?
Oh,
Yeah. But we didn't. Worked out in the end.
we were not York
For
University.
which I was very grateful considering I started classes.
Well, yeah, we were all grateful. I get on strike before. It's no fun. It is no fun. I was on strike at Memorial. We played ball hockey in the ticket line. We had a 40-gallon drum with a fire in it, because, if you don't have that, it's not really a strike. Well, the first day on the picket line, I said, where's our 40-gallon drum? With wood for a fire? Why are we not, are we a union? And I was kidding. And of course, the next day, somebody brings a fire. Playing ball hockey. It's like, what do you do? It's cold out. It's in Newfoundland. Play hockey. We're Canadian. All right, so this is really, and I know you guys have run into this stuff before, this is to get you ready for the final topic, which is going to be multiple regression. And what we're going to do there is we're going to have more than one predictor. We're going to have more x's, right? So we're just going to have one y to predict, but we're going to use more than one x. So when you think about that cigarettes per day thing, it's not just going to be one variable. It's going to be, well, in fact, the model he came up with had 4 predictor variables. And all these different slopes. We can stop thinking of the slopes shortly. So that just becomes an equation. Any questions on this stuff? Because I want to make sure you get this. Because if you get this, then you'll be fine for the final topic, which is, I guess I call it a multiple regression. Yes, please. I forgot to bring your quizzes. I'm sorry. Yes.
Can you explain to me how the error equals 0 again? Why and when I would use that?
How do you mean? This here, the residual plot?
Yeah.
Right. So 0 is right here. Okay? And it should overpredict as much as it underpredicts. Yeah. So it should predict, it should overpredict as often as it underpredicts, and as much as it overpredicts, it should underpredict, and also there should be no relationship between what the x value is and if the value is underpredicted or overpredicted. It should be completely random. It should be like, here's a nice line. We should get something like this. I mean, it's never going to be this beautiful. Nobody collects data for that pretty. But you see what's happening here is the line is overpredicting as much as it's underpredicting. So when it's overpredicting, it's this one here. And when it's underpredicting, it's this guy here. But when we sum all those residuals, all the y minus y hats, we should get 0. The square. When we sum them all, we get 0, but if we sum the squares, we'll minimize them. Because we want to make our prediction mistakes, because they're errors, as small as possible.
So if the computer if I put my data in, then the
Yep.
computer produces that, and
Yep.
when I do a linear regression,
Yep.
then basically I know the computer's done it right, and
Yeah.
that should be 0. So when would I use that?
When we use width, well, sorry, I know you've lost me. No, it's okay, but I want to help because I want to help.
Yeah, I'm trying to
Hey.
figure out when I would need to check that.
Oh, this over here?
Yeah.
Right now, I wouldn't worry about it. It's just a thing to get you used to the idea of what a residual plot is. Right now, what you do is you have a scatter plot of the 2 things that you'd see. Is it a straight line or not? When you start doing what's called multiple regression, you start having more than one predictor, you stop having straight lines, you stop having just lines. You've got a thing you may not be able to imagine, which is, and you think, okay, well, it's like a 4-dimensional thing. So instead of a line now, it's a whole model, a
Okay.
linear combination of a bunch of things.
Yeah.
That should overpredict as much as it underpredicts. And that's when that matters.
So that ends up being like a 3D tube. Is the line through it?
Yeah, it's not necessarily going to be 3D, it could be 9D.
Oh.
Yeah.
Oh.
Yeah, so you can't imagine it anymore. But you can turn it into something that's 2-dimensional, which is the error, the predictions, and then you use the whole model like that, along that axis instead of x.
Oh, okay.
Yeah. Yep. It's a good question. All right. Other questions? No, it really wasn't a question. I'm not just saying.
I appreciate it. I think you are. Thank you.
No, I'm really not. And I forgot your quizzes. I'm sorry. I do actually have them in my office. If you made your homework assignments, I did them all. How hard is that? All right. There's also an assignment on the website. You can take a look at that if you wish.